We made a digression. We came to minimum mean square estimation. First described what it is. We'll review it, and then we saw the basic equations, and then suddenly realized that to compute the optimal weight, we need the correlation vector. I mean, we need the correlation matrix. So we don't know how to get the correlation matrix. So we said that okay, let us stop here, and we went back and found out how to estimate the correlation matrix, and as a natural consequence of that, we also saw how to estimate the periodogram, right? And after that, we had some confusion about Z transform, so we thought that okay, we'll again review the Z transform convergence, etc. And we had also reviewed the concept of eigenvalues, eigenvectors. They were all with a purpose. The basic purpose is that we want to go slightly deeper into linear minimum mean square estimation, because it is one of the very important and central topics, and widely used for a variety of applications, from speech coding to target tracking to I mean all sorts of applications, matched receivers for communication channels. In n number of applications this theory is used, right? So we wanted to understand, we want to go a little bit inside and see, gain some analytical depth into it. So whatever we did was to get some of our basics again shaken up, and so that now we can see. So we are now we are coming back to the analysis, and this analysis in many cases will involve this concept of innovation. Okay, this I mean if we'll see that if we try to express things in terms of innovations, then the analysis becomes simpler and easy to understand, and it's absolutely equivalent. I mean, seeing so we need to understand this concept of innovations at this time. It is a very central concept, and lot of analysis is actually done in terms of it, right? So let's get into it. First of all, just because we know that memory has a time constant, which may be short or long, depends on people. So we are just getting back to little bit recapitulation on eigenvalues and eigenvectors. We have done that. So we just want to recall that if you have a symmetric matrix R, then RQ is equal to lambda Q. This is an equation where Q is a vector, R is a matrix, lambda is a number. So m into m into 1 becomes m into 1, and this is a number into an m into 1, so dimension is matching. So the vector which satisfies this for some lambda, this lambda is also not arbitrary, it is a particular lambda, then that lambda is actually called an eigenvalue that can be solved from this equation, determinant of r minus lambda equal to 0. For example, here we had worked out an example. So if you have r as 1 2, just a simple example, then this equation becomes like this, and we can solve it. It will become an nth order polynomial in lambda. So we can solve for lambda, and we will get n roots. If it is an nth order polynomial, we will get n roots. So corresponding to those lambdas, if we solve this equation, we can always solve this equation. This side now, so this, then we will be able to solve for this q. So this q will be called the eigenvector. Okay, we need to understand eigenvalues and eigenvectors and some of their properties, because this is widely used in our theory, and these properties are very interesting. These properties say that for distinct eigenvalues which generally occurs, these eigenvalues and eigenvectors have very desirable properties. So one of the properties which is very key property is that these each eigenvector is actually, all the eigenvectors are actually orthogonal to each other, they are actually perpendicular to each other. See, if you have a vector r and if you have another vector q in an n dimensional space, then how do you express the fact that r and q are perpendicular? By executing a dot product. So this is nothing but a dot product of the vectors. So it says that the dot product is 0, right. So which says that these eigenvectors are actually perpendicular vectors, which immediately tells us that we can define, you know, this is, we are actually talking about m dimensional vectors. So we have an m dimensional space. Now if you want to, it can be defined in terms of some arbitrary x, y, z coordinate axis, but what we are saying is that the moment we have found that we have got these vectors in this space q's which are perpendicular to each other, that immediately tells us that we can probably define a coordinate system in terms of q's. Normally when we define a coordinate system, then we need a, for example, to define a 3-dimensional coordinate system, you need 3 vectors which are, ideally speaking, which are mutually independent, you know, linearly independent vector, that will do, but then just for having, you know, convenience, so that one doesn't have a component on the other, we want them to be perpendicular. So here we have got a set of perpendicular vectors in that space. So that immediately tells us that, okay, now we can choose, suppose we choose these as our coordinate axis, do we get some advantage? We get a lot of advantage, as we will see, right. So remember that we will be very interested in using these as our coordinate axis, and given any random vector, describe them in terms of these vectors, right. We will do that very often now. And if you, I mean, just as a consequence of this, that these are orthogonal, you see you have these 2 results, which says that the matrix R can be broken up like this, where these, what are these q's? These q's are basically a matrix whose columns are these vectors. So this is q1 to qm. You can imagine q is an m into m matrix, q is a square matrix. So it has m columns, so each column is a vector, and these vectors are the eigenvectors. So if you take the eigenvectors and put them one by one and then make a matrix, that is q, and so now R can be always expressed as q gamma q transpose, but this gamma is going to be a diagonal matrix. That's very advantageous, that is going to turn out to be a very advantageous thing for us, because gamma is going to be diagonal. That we will use in n number of, I mean, we will use it to a lot of advantage, but just let us remember that at this point there are very interesting properties of this matrix, that first of all, any matrix R can be now broken up into this form, where gamma will be a diagonal matrix, and not only any diagonal matrix, the elements of gamma will be the eigenvalues. So gamma will be this, so it will be lambda 1, lambda 2, lambda 3, lambda 4 as a diagonal matrix. And not only that, these matrices are such that q inverse equal to q transpose. It turns out, again because of this, just multiply q by q inverse. So q inverse should be equal to should be the identity matrix. Now you multiply q transpose. So if you multiply q transpose, you will get terms like this. That is, the ijth element of q transpose will be terms like these. So then immediately you can see that all the off diagonal terms for which I and j are different, they are going to be 0, and if you choose the length of I as 1, that is norm of that is q is a vector, qi is a vector, it has n components. So you just choose them such that root over q1 square, q11 square, rather qi1 square, qi is a vector which has elements qi transpose, qi is a column vector. So qi1 up to qim, these are the elements of this vector. These are these are numbers. So if you choose these such that root over qi1, sorry you cannot see perhaps, that is just see that what is the length of this, root over x1 square plus x2 square plus x3 square, that is the length of this vector. So if you choose the length to be 1, then all the qi transpose terms will give you 1, so it will be an identity matrix. Therefore q inverse will be equal to q transpose. All are properties of this thing, this is the key property, right. So these are some of the properties of these eigenvectors which are very useful for us, which are going to be. So we will now use these properties to our advantage. So first of all let us try to understand what is innovation. See, in English innovations means what? It means that, I mean, you actually generate something new, something which was not existing, right. I mean, I remember I read the what is the difference between discovery and oh no, that was invention, that was different. So in any case, I mean, innovation means which is something new which has been generated which was not there, right. So here, so in this sense the word is used. So why the word innovation has been used? That's because, so let us try to understand this. Suppose x is a random vector of any length, it has some components x1, x2, x is a vector, so it has components. Now suppose from x multiplying by a matrix A, I can generate a vector W. One vector multiplied by another vector will give, multiplied by a matrix will give me another vector, right. Now in a sense these W's have been generated from x, so they contain so there is no new, whatever information is there in x you have used that to generate W. So W contains the same information as x, you can say. Now if you can generate this W in such a manner that this RW is diagonal, expectation of W transpose is diagonal. What does that mean? It means that Wi, it means that what are the elements of this? The elements of these are, that is the ijth element of this matrix will be expectation of Wi Wj transpose, is it not? What is this is a vector, this is a vector, actually this transpose actually Wi Wj. Suppose W has elements W1 up to Wm, here also W1 up to Wm. So now you are multiplying a vector, a column vector by a row vector. So what will be the I, so this will give you a matrix. What is the ijth element of this matrix? It is Wi multiplied by Wj. So expectation of the ijth element of Rw is this. Now we are saying that Rw is diagonal. What does it mean? That Wi Wj is equal to 0 for I not equal to j. That is what we are saying. That means that the element of W are uncorrelated, which means that now each element has no bearing with the other, each component. So as if each component carries some new information which cannot be obtained from the other. So whatever information Wi holds, it cannot be generated from Wj or all the others, because Wi has no relationship with any other Wj. So it contains some unique information which is new, which is not there in the other components. That's why this vector W will be called an innovations vector, where each component of it will now see it, the elements of x were kind of mixed up. That is, x1 may have some correlation with x2, may have some correlation with x3, it may happen. But which means that the information that x1 contains, at least part of it can be generated from x2 because it is correlated with x2. But that does not happen in the case of W. So by transforming x, I have generated a vector W where the information is kind of compartmentalized. Some information in W1 and some information in W2, some in W3. Each of them are new information. One cannot be generated from the other. So in that sense W is the elements of W are the innovations. Okay. We will presently see what is the advantage of dealing with such W. So there are two facts that we must remember, that as far as the information is concerned, this vector W is perfectly equivalent to the total information of X, because it has been generated from X. So all that in the information that is contained, I am using the term information in a vague sense, but I mean I have not defined the term information, right, mathematically, but what I am saying is that in a statistically average sense, components of X can be generated from other components of X. In that sense there is overlap of information. Okay. So all I am trying to say is that you have been able to generate a vector which overall contains the same information as that of X, but now the components of the vector are each one contains new information by transforming it by a matrix. This is what I have done. Now let us see what is the advantage. Now first of all let us see how to generate this A. I have not defined this A. I have not told what A will actually achieve this. So now we will see that this A will be again in terms of the eigenvector matrices. So now, this is sometimes called an Eigen decomposition. That is, if you decompose a vector in terms of the eigenvectors. So let X be a random variable. You can assume that it is with some mean. If you assume it has some mean, then you have to define a new variable which is x minus mu x, transform it to a zero mean variable, or you can start with a zero mean variable, either way it is okay. And Cx is the covariance matrix of X. Now, so Cx is like my Rx. I just use the term C because X I assumed with a non-zero mean, so I should say covariance rather than correlation. But Cx is nothing but correlation of X naught. Same thing. Now, so that is my Rx that I considered. Now I can find out the eigenvalues and the eigenvectors of Rx, and I can stack those eigenvectors to make this matrix Qx. This is the Q matrix that I was talking about, which consists of the eigenvectors of R. I have stacked them up, and then now if I will show you that if I make a transformation like this, that is, if I choose this as the A matrix, then RW will become diagonal. That is simple, because if I define this, then what is the expectation of W transpose? It is simply this. This is my Rx0 transpose or Cx, whatever. So now I have Qx transpose Rx Qx, which is nothing but gamma x. That is my previous relationship. So you see that if I now transform this by this eigenvector matrix, I get the innovations. Right? That is why we needed to know what are eigenvectors. Now, okay, so I have been able to generate innovations. So what? Why should I generate innovations? What is the advantage? There are various kinds of advantages. One big advantage is analytical simplicity, but there is some practical advantage other than conceptual advantage. That is, so I will show you one of the advantages which is very much used in what is known as coding. Okay, what do you do in coding? Suppose you have a signal, right? Suppose you are saying that we know that any signal can be represented as what is known as in terms of a set of standard signals. For example, we try to represent a signal in terms of sine waves, right? So sine waves are our standard signals, and we try to express the signal in terms of a sum of sine waves, right? Sine waves are not the only ones. There are many other kinds of waves, many other kinds of what are known as basis functions, in terms of which you can break up a signal. Okay. Now, suppose I am saying, suppose I have decided, suppose I have think of a transmitter and a receiver. So I have to transmit a signal x from here to here. Okay. Now I have some bandwidth constraints, that is I want to reduce the amount of data that I want to transfer. This is a very important requirement. Suppose you want to have video conferencing, so you have to send real time image data over the network. Each image data is going to be a say 1024 by 1024 pixels. So huge amount, if you want to send the raw data, huge amount of data will have to be sent, and it's completely, I mean it's not necessary at all, because especially because in video conferencing you are not really trying to measure what is the distance from the left eyeball to the tip of nose. These kind of measurements you are not doing. The whoever will see it, he or she should be comfortable, should be able to understand the speech and the motion, that's all. Reasonable accuracy. So firstly remember that there is no need to transfer each pixel for this application. Now the question, so now come back to this question that I want to transfer a signal from here to here. I don't want to transfer everything, I want to transfer some approximation of it, and I want to, using those approximations I want to get the best accuracy once I build up the signal there. So I want to send something, some small data from here, I want to code the signal, send the codes over the network, and then using the codes I want to decode it at the receiving end and get back my signal. This is a very important requirement in communication. So now suppose that I am trying to send, suppose I have a signal x which I want to send. Okay. Now signal can be anything, so it's very difficult to, so we can assume that it is going to be a random variable. For example, speech signal, have you seen speech signals? They are very much look like random variables. So I have a, so now the question is that suppose x is a signal and it can be represented on a set of basis vectors. So suppose x is a random vector, it can be broken up into some coordinate vectors. So these are my coordinates and these are my coordinate vectors. I can always break it up. Suppose x is such that you have I is equal to 1 to m, that is x can be broken up into a set of such m components. Okay. Now the point is that rather, so what you can do? What you can do is, if you know that suppose the transmitter and the receiver at both ends, if these vectors ai's are known, if they have decided that I am going to use the same coordinate vectors, then I don't need to transfer x, but rather I can transfer these wi's. I can send these wi's. Then at the receiver end they will calculate this sum and they will make x. Now the point is that what is the advantage of sending the wi's over this x? No advantage, because x contains m coefficient, this also contains m coefficient, so I am not getting anything. So I want to send less number of wi's, right? So suppose I want to send small m number of wi's. So then what will the receiver do? Receiver will have to do with this small m number of wi's it has received. So it will have to reconstruct it using this now less number of terms, and it will in general construct an approximation of x, and this will be the error. Now I want to choose these ai's such that this error is the least. This is a very valid problem. So I want to send, suppose the vector can be actually represented in terms of 300 components, I want to send only 30, and yet I must choose my basis vector in such a manner that yet when I reconstruct I will get the least amount of error. What I can do? Okay. So what is error? Error is nothing but I equal to 1 to m is there, so I equal to m plus 1 to m, that is the rest of the things that I did not send. Now I find the power of the error, that turns out to be this ai transpose this A matrix we will definitely choose as what is known as an unitary matrix, that is A inverse equal to A transpose. Note that in our case Q inverse was equal to Q transpose. but so the eigenvector matrix is a unitary matrix, but there can be other unitary matrices which are not eigenvector matrices. So this I am doing because I want to, I mean I can get these Wi's very easily just by invert, that is if W equal to A transpose X, X will be equal to AW because A transpose is I. So just by transposing I can do it. So now it turns out that the expectation of E transpose E becomes this one, that is, so the error is actually the power of those components which I did not send, right. Now, so now but then this, what is my original problem? Or my original problem is that I want to minimize this MSE. I am given X, I want to minimize this MSE and I want to choose these AIs. That is my problem. Okay, subject to this requirement that AI transpose AI is equal to 1 and AI transpose AJ is 0. Subject to these constraint, I want to minimize this function. So it is a constraint minimization problem. Do you remember what we do when we have a performance function and we want to minimize it and we have some constraints? We use what is known as Lagrange multipliers. Basically it's a way of seeing it, that is we convert the constrained optimization problem into an unconstrained optimization problem by adding these additional terms. These will give us, and then I will differentiate it with respect to these which I want to optimize. I want to find out AI, and I will synthetically, that is artificially. So actually I should not use this, this here lambda has been used because lambda turns out to be an eigenvalue, otherwise normally it can be anything. So we should, if we differentiate it with respect to these variables, we will get back the constant equations. So which means that this pi equal to 0, which is my unconstrained, if I want to optimize something with respect to AI, what I have to do? I have to differentiate with respect to AI. This is nothing but a vector. This means that this is nothing but a del p by del AI1 del p by del AI2. This is a vector. P is a scalar. I am differentiating a scalar with respect to a vector. So what does it mean? It means that if the components of the vector AI are AI1, AI2, AIM, then this term, this is nothing but a notation. This notation implies this vector del p by del AI1, del p by del AI2 and so on. This vector is denoted by this symbol. So we have to find that this equal to 0 solution, and not only that we have to solve for this and these, because these are my constant equations. If you just recalling Lagrange multiplier. So if you differentiate it, you can see it is, you can, if you want, you can take a 3 by 3 vector and actually write out this term and then differentiate. If you want to use scalar theory, but it turns out that if you differentiate this term will give you Rxai and this term will give you lambda I. This is like x square. Okay. So now you see that if that is so, what is this equation? This is that old eigenvalue eigenvector equation, if you see. So which means that for minimum mean square error, these should be eigenvectors and these should be eigenvalues, right? So now see the importance that if you want to send less number of components and still commit the least amount of error, then you should decompose when you are sending those Wi's, you should do it on the basis of eigenvectors. Then if you, now which eigenvectors? Obviously you should send it such that this sum is the least, is it not? So obviously you should send those components, see each component Wi is corresponding to a particular eigenvector. So it will turn out that you should send those components which correspond to the largest eigenvectors. So send those components. So first send the largest eigenvector component. Second, next send the largest eigenvector means that eigenvector which corresponds to the largest eigenvalue. See, the eigenvalues are all real because R is a symmetric matrix, symmetric positive definite matrix. So therefore, you can order the eigenvalues. So one will be the largest, then the next, then the next, then the next, and so on. So first send that component which corresponds to the largest eigenvalue, then send the next one, then send the next one, then whatever finally whatever will remain will be the ones which are whose power, that is the power of the error will be proportional to the power of the remaining eigenvalues. That is what it says. So you see that this first thing is that this eigenvalue eigenvector decomposition is good for making the best reduced order approximation of a signal. If it really needs a large number of coefficients, and if you want to approximate it using a small number of coefficients, then it should always be done based on an Eigen decomposition. That is the first important thing.
So in the previous page, AI transpose equal to AI equal to 1 means?
AI transpose AI equal to 1. Length of the vectors should be equal to 1. AI is a column vector, so AI transpose AI means what? AI 1 square plus AI 2 square plus AI 3 square plus AI 4 square, like that. AI transpose AI equal to 1. See this one. Okay, so now let us come back. This is our lecture 11, if you see, where we studied minimum mean square estimation. Now we can have some more insight into that. So let's recapitulate that little bit. So what did we say? We said that we have samples of some things xk, and we have another thing y, which we may not be able to measure, okay, but we want to estimate y based on xk using linear estimators, such functions. We are not going to use log something, we are not using those functions. Okay. So what is the best? So ideally speaking, if I say that okay I can use maximum m number of components, then this is one way of saying that, and here I have assumed that this is a, here I have assumed that there are k number of variables, that is x is itself a vector, so it is slightly more complicated, but the basic problem is that you are given a set of, you are given some signals x, based on its samples you want to estimate some other signal y using linear functions, such that the estimation, that the minimum mean square error in estimation occurs. This is the linear minimum mean square estimation problem. You are given one random process, you want to estimate another random process based on the samples of this random process using linear estimators, such that the mean square error is minimum. So there are, in any estimation setting there are three quantities. One are the sets of random processes, that is you have some observations, you want to estimate something else, so what you have and what you want to estimate. Then you have some structures of estimators. You normally do not say among all possible estimators. That is not useful, because the set of all possible estimators is so vast that you can never explore it. So we restrict ourselves to some kinds of estimators. In this case we are considering linear estimators, all right, and we define a performance criterion, that is how do we decide whether estimator A is better than estimator B or not. So we say that our performance criterion is mean square error should be minimum. So you have a model set, that is an estimator structure, you have a performance criterion, and you have some signals. For any estimated setting these things are required. Okay. So what did we see? So we wrote the performance criterion like this. See, this is the error. So error transpose. So this is my expectation of error transpose should be minimum. And then we said that, then we found that we can that this will be minimum if this equation is satisfied. Okay, this is sometimes called the normal equation. This is sometimes called the normal equation, which you have to solve if you have to get the optimal weight C. Then you will get the minimum value of this performance criterion. Very simple. You can obtain it by just casting it like this, or you can obtain it by differentiating. Either way it is okay. Now we also found out that if you use the optimal estimators, then also you will get some error. It is not that if you use the optimal estimator you will get 0 error. You don't never get 0 error, you get some error. But the properties of the optimal estimator is such that you have what is known as the principle of orthogonality. That is the error components are going to be perpendicular to the estimates, that we had also seen. Okay, we'll come back to that. That has also very interesting properties. So let us see that. Okay, now let us see that. So what did we find? That for a given, suppose you choose an arbitrary weight C, then what is going to be the error? This is going to be the error, total thing. If weight C was equal to C0, that is the optimal weight, then this term will be 0. This last term will be 0. See, last term is always positive because R is a positive definite matrix. So therefore, if you multiply with any vector x transpose Rx, R positive definite means R inverse also positive definite. So if you multiply it by any vector x transpose Rx, this it will generate a positive number. So this number can never be less than 0, which means that this sum must be always more than this, because this is positive, which means that this is the minimum error power that is possible, and that will occur only when RC equal to D. So that is the optimal minimum mean square error, when this will be 0. Correct? Now we want to see that how these errors are distributed. That is, how first of all how these error surfaces look. We want to look a little bit on this error. You know that if I want to study that I know what is my optimal weight error. This is the minimum possible. You cannot obtain using linear estimators less than this. Now I want to see that if I am away from the minimum, if my weight estimate is away from the optimal estimate, then I get some penalty because my performance index increases. Now I want to characterize that, okay, if my deviation is on this side, whether the performance penalty will be more, or if it is on that side, performance penalty will be more. I want to understand that how this performance penalty varies if I deviate from the optimal estimate by a given amount, say on that direction or in this direction. That I want to understand. Okay. So for doing that, I use Eigen Decomposition. So I divide R into, again like this. These are the Eigenvector matrices of R. So these results we have already seen. This will become diagonalized. This Q transpose Q is I. These results we have already seen. These are just properties of the Eigenvector matrices. Now I see that suppose this was my penalty. So my delta PC, and now what is this? This is my PC0, this term. That is, if C was equal to C0, this would have been the penalty. That is the minimum. And this one I can actually cast like this. This is simple. You just multiply RC minus D by R inverse. You will get, see here it is R inverse has become R, and here R inverse will come. That is easy to see. So now what is R inverse D? R inverse D is C0, because RC0 equal to D, that is the equation C0 should satisfy. So this is C minus C0, this is my deviation vector, this is my optimal weight vector, this is my given weight vector, so this is my deviation weight vector. So my penalty now I have expressed in terms of deviations from C0. Okay. Now what is R? Now I make I am making an Eigen decomposition like this. So I find that if I defined a new vector V which will transform this C minus C0 by this matrix, what does it mean? That I am trying to express taking these components of C and then express it in terms of the perpendicular component, that is the eigenvector coordinates. So if I express V in terms of eigenvector coordinates, then my error is actually expressed like this, because now this will be my V and this will be my V transpose, rather opposite. No, this will be V transpose and this will be V. So it is V transpose gamma V, gamma is diagonal. So it is nothing but lambda k Vk square, lambda k are the eigenvalues of R, so they are the elements of gamma. Elements of gamma are lambda 1, lambda 2, lambda 3, lambda 4 that we have seen. So this, now the penalty can be written as a, what is the advantage? The advantage is that now they have become decoupled, that is now it has become a scalar sum. These Vk's are now scalars. It is actually Vk transpose Vk. Vk transpose Vk means length of Vk. So if I now see the diagram. So suppose this is C0 and this is my vector C. Suppose I have only using two vectors I want to estimate. So my weight space is now 2 dimensional. So I have a C1 C2 weight space in which my optimal weight is C0. Now if I choose some other weight C, which is this vector, this is my delta C. Now suppose this is my one eigenvector, rather q1, and this is the other eigenvector q2. So if I now project this vector in terms of this will be my v1 and this will be my v2. That is, this vector I am trying to express in terms of these coordinate systems. They are also orthogonal coordinate systems, I can always express it. So now the error becomes a function of v1 and v2, that is the constant error surfaces are ellipses. What is the equation of the error now? That is the penalty in error. It is lambda 1 v1 square plus lambda 2 v2 square. So that is the equation of an ellipse on the v1 v2 coordinate system. So now these are my constant penalty contours, and from this I can see that if I make a small error here, then my j will go up more. That is, if I want here, that is on the v2 axis, I have to go more for a given amount of error, but here I have to go less, which means that this axis is actually more sensitive to error, which means that I should be more careful about weights on this axis rather than on this axis. This axis I can do little bit of error, performance index will not increase so much. So you see that just by decomposing it on the eigenvector, I can now get this insight that on which side I can make errors and on which side I cannot. No, it will be more penalty. It will give me more penalty. Later on we will see that when we will discuss adaptive filters, we will see that if I want to adapt the weights, change the weights, how do I prove whether this adaptation mechanism is going to be stable? How do I know that these weights will not explode? So I have to prove certain things, and then breaking onto these coordinates will simplify matters to a great degree, in the sense that we will get scalar differential equations rather than vector differential equations. So you see that by breaking up my error, I can characterize penalty in a nice manner. There is one last point which I want to discuss, that comes from what is known as the principle of orthogonality. What does it say? That this optimal estimate, that is, if you choose the weights as C0, it has a very nice property. What is that property? That property is that the error, see, this is the error if you use the weight Now the error becomes uncorrelated with the estimate, that is the estimation error is uncorrelated with the estimate. Now what does it mean? Let us see it in a particular case. Okay, so we had, for example, suppose consider this problem of prediction. Okay, what do we want to do here? We want to estimate, this is a very standard problem, that you are given some data infinite past from 0 to n minus 1 and you want to estimate yn before it occurs. It's a very common problem. For example, adaptive noise cancellation. So I don't have the noise sample, but before that I must estimate it and generate another sort of anti-noise which will kill the noise. That's what I want to do. So linear prediction is a very common problem. So just consider this problem. Only thing is that this is, I have considered this to be infinity, which is done when you have a Wiener filtering problem. That is, if you want to estimate it using an IIR filter rather than FIR filter, then you will get an infinite number of terms. That is always true because the IR filter has an infinite impulse response rather than a finite impulse response. So now, but still it's a linear estimator. So you have a number of weights, and so you will have an error, and if you use optimal weights which are given by the Wiener filter equations, then what will happen? What will be the property? That the principle of orthogonality will say that En will be orthogonal to y hat n. Now you see, y hat n you have generated from what? You have generated from y0 to yn minus 1. So as if you have extracted whatever information you could from the measurements of y0 to yn minus 1 to estimate yn. So all the information from y0 to yn minus 1 has been extracted into y hat n, but then yn will have some new information. So this error represents that new information which is in yn but cannot be deduced from the past values of yn. So it's a new information. So it's an innovation, right? So it turns out now obviously since innovations are going to be uncorrelated, now so that's what I am going to prove. So the principle of orthogonality says that this must be orthogonal to y hat n, okay, and y hat n is nothing but functions of past samples of y. So en must be orthogonal to all the past samples of y for all I, right? If you have this, then you can also say that all the errors, that is, you are getting at each instant you are getting an error, y1 minus y hat 1 is e1, y2 minus y hat 2 is e2, and so on. So you are getting e sequences. Now these e sequences are mutually uncorrelated, because what is en into en minus y expectation? That is en into yn minus y hat n minus y, that is the definition, and y hat n minus y is again has been generated from the past samples, but then en is uncorrelated with all past samples. So therefore this term is also 0 and this term is also 0. So therefore these are innovations, and they are like we had learned that innovations must be uncorrelated. So they are indeed uncorrelated. Okay. So now what did we see? We said that if you have a data sequence y1, y2, y3, y4, it has some information. We had said that we can transform this vector into a set of innovations which will contain the same information as this sequence, but between them they will have no information overlap. That is, E1 will have some new information, E2 will have some new information, E3 will have another new information. Together, E1, E2, E3 for all together, they will contain the total information which is there in y1, y2, y up to yn. Only thing is that information is now compartmentalized, which is not there in y's, right? So the sequence En is uncorrelated with all its past samples, and these are the innovations, okay, and they are white. This gives you a fundamental property of linear MMSE estimation, that innovations must be white. So you know that you have really reached optimality. For example, suppose you are this happens in adaptive filtering very often, that you are trying to adapt these weights and then trying to come to the optimal weight. Now how do you test whether you have come to the optimal weight? By testing the innovations. So at one point, if you find that the innovations are becoming white, then you know that you have reached the optimal weight. This is a standard test of determining whether the set of estimates have converged to the optimal weights, right. So we will have, and this is just 1 minute. This is just this is a standard mathematical procedure called Gram-Schmidt Orthogonalization. Yeah, don't get it has a very high sounding name. Okay, it merely tries to say that the innovation sequence you can easily generate an innovation sequence just by simple substitution. For example, suppose you are given a sequence x1 to xm. How do you transform it into a set of innovations which will contain the same information as x but will be uncorrelated? How do you construct it? So it's very simple. First take omega 1 equal to x1, the first sample, take it equal to the first sample. Then suppose w2 is x2 minus this. So you are subtracting the w1 first component by multiplying by a weight and then subtracting from the second sample. That you are assuming as w2. Now what will be the weight such that these two will be uncorrelated? That is the question you are asking. You are asking that how do I choose this weight such that these two are uncorrelated? So if you solve this equation, this expectation of w1 w2 equal to expectation of w1 x2 minus this, that is equal to 0. So then if you choose the weight is equal to this will be 0. So now you have got the second innovation element which is uncorrelated with w1. Now you choose the third. So the third should be uncorrelated both with w2 and w1. So you now get two equations and you have two parameters to solve for. So you solve for the parameters and you get this. So in this way you can go on doing. Then you will get a set of sequences w1 which have been generated from x1, x2, xn. So they have the same information but they are uncorrelated. So these are the innovation sequences corresponding to this. All this is being done because, as we shall see, that for many filtering problems what we will do is, first suppose I want to generate x from y, necessarily what I will do is, first of all from x I will generate an innovation sequence. I will make x white, that is called a whitening process. So from x using a filter I will first generate some white innovations, then from the innovations I will go to y. This gives me a clear picture of what is happening. Rather than going directly from x to y, we will, especially when we have infinite number of terms, etc., we shall often go in two steps. First we will whiten the innovations, then from the white innovations we will go to y. So we will come to that step in the next class.